So one thing we didn't talk, we talked a lot about, well, we talked a little bit about dissolving a solid solute in water, remember? And there was this, like, gosh, were there six different salts that looked at the effective temperature on solubility? Well, what about if you dissolve, what if your solute is a gas instead of a solid? Okay, so that's what this is. So basically, usually if you dissolve a gas solute in a liquid solvent, okay, usually it's exothermic. We know it's exothermic because I put heat over here. Okay, one of the things I would introduce you to, Le Chatelet's principle, we're talking more about Le Chatelet's principle, but it's kind of like, and this is a first semester, think of a poke or a pull, you know, push or a prod or a pull. So in this case, if we add heat, then what it's going to do is poke. And what it's going to do is poke actually the formation of what's over here on the left. And what's over here on the left is breaking out the individual, the gas is going to basically come out of solution. Okay? So with the addition of heat, okay, addition of heat, basically your gas will be less soluble. If you cool it down, your gas will be more soluble. Fishing, right? I've heard it described that in nice cold water, actually your fish can be nice and lively, and it's not because they're so cold. One of the reasons it could be is that your actually colder water can have more oxygen dissolved in it. Have you ever, and maybe you have, but you haven't necessarily paid close attention to it, gotten a cup of cold water from the tap? Okay, so you run your water so it's nice and cold. Okay, you come back maybe a couple hours later and it's at room temperature. Have you ever seen the little bubbles along the side? Okay, that's basically gas that was dissolved, okay, but at the higher temperature it's less soluble. Okay, so that's generally how that goes. So the solubility of most gases will decrease as the solvent gets warmer. Okay, most gases. So case in point, we're just kind of looking at oxygen dissolving in the solvent water at different temperatures. Okay, so its solubility at 0 is 14.60 parts per million, and look how it gets warmer and the solubility goes down. Okay, that's significant. Well, I don't know. A difference of, yeah. Okay, so solubility is decreasing as temperature is increasing. Very good. So you already did these. Okay. That's always nice to get to an assignment slide where you've done that. Did you have anything handed, Matt? So on to Henry's Law. Henry's Law has one of my favorite pages. Hope it works. Henry's Law is one of those, that makes sense sort of thing. And Henry's Law on the heels of, this is part 10, on the heels of part 9 is just perfect. Because part 9, last we talked about, was a gaseous solute dissolving in a liquid solvent, gas dissolving in the liquid. That's exactly what Henry's Law is talking about. Okay. But what Henry's Law is talking, well, that's what it's talking about. So here is one of my favorite, I was trying to pause it here for that. The fact that when you know, we can look at this bottle that looks like it's been open, see what they're open. You're fine. But before you drank any of it, there was like a little clear space at the top. So you have to buy into the fact that in that little clear space, what they did when they got any pop ready to go is they just shoved it full of CO2 gas. They pressurized it with CO2 gas. And Henry's Law says that basically how much CO2 gas can be dissolved in that sugar water is a function of the partial pressure of the CO2 gas that's being shoved at the very top. So to me, it's, I usually use the word headspace. We're talking about a little headspace above the liquid. It's pressurized, okay? And Henry's Law says, you know, you can adjust the amount of CO2 that would dissolve in sugar water by just monkeying with that pressure. You know, you make it light, not much CO2 dissolves. Make it heavy, a lot of CO2 would dissolve. Okay, so Henry's law is a short little equation. I'm going to show you. It's on your sheet that I gave you for your test. Basically, it goes like this. Okay, kind of nice, short, sweet. That's Henry's law. Sometimes, and I'll go ahead and add it up here, instead of, this is basically the solubility of the gas. I know it says C, but C stands for concentration. Concentration or solubility of the gas. It can be in terms of moles of gas per liter of solute. It can be terms of grams of gas per liter of solute. Okay, I've never seen it really amount of solute per liter of solution, I should say. I've never seen it amount of gas per amount of solvent. I never have. But sometimes you'll see that as S, as in solubility of the gas instead of C. Either one of those. So P over here is the partial pressure of the gas in the headspace. Okay, so that is the partial pressure. I'm going to say in headspace over liquid. And K sub H is Henry's law constant. And honestly, I'm going to go ahead and say it right here. Sometimes when I work problems, and I'm going to show you some example for your own homework, you can calculate Henry's law constant. You can't calculate all constants. But oftentimes, this is often you calculate it. Because notice, we can get Henry's law constant is all we got to do is what? Take the solubility of the gas divided by the partial pressure of the gas. The concentration of the gas, C sub gas, divided by P sub gas is equal to KH. So you can come up with that. But, okay. So here are some common, however you use Henry's law, your units need to be consistent, especially with regard to concentration of your solute in your solution. So very common units would be concentration in moles of gas per liter of solution. You can either use millimeters of mercury or atmospheres for partial pressure of gas. And then Henry's law constant will kind of fall into place from there. All right. So it's one of those constant that depends upon a lot. These are three very big things. Your Henry's law constant depends upon your gas solute. Okay, it depends. It's not always water. You're not always dissolving a gas in water. You could be dissolving the gas in something else, and it also depends upon temperature. So it's very picky. But like I said, if you have the concentration, you have C at any partial pressure, you can knock out a Henry's law constant for that particular gas and solvent at that temperature. Okay, so these, let's kind of see how this goes. This is saying that your solvent is water, your temperature is 25 degrees Celsius. And then it says at an assortment of gases as your solute. Okay, so it says nitrogen, you can get 8.42 times 10 to the negative 7th moles per liter of N2, okay, in water, okay, per millimeter of mercury is your partial pressure of your O2 headspace. All right, so again, this kind of goes back to the bottle of pop back there. Seltzer water, right? Carbonated. The headspace we were talking about then, you know, it's just so maybe even overlooked. Okay, but that is where your P sub CO2 would then have an impact on the solubility of CO2. Okay? And the problem, the reality is of course when we open a bottle we hear it fizz. And of course the partial pressure of CO2 goes from very high to basically nothing. And so we start the kind of, the CO2 gas starts migrating out. So from left to right, I forgot I did this. Makes you want to go do one of those Mentos experiments. Not a real experiment, but I've done that before out on the Mentos and pop. So solubility and pressure. This is kind of clever. So basically the gas solute is blue particles. You can see it here as a gas, and you can see some of it is dissolved in the liquid here. And like we've done before, if you go ahead and basically pressurize the gas in the headspace above that liquid, as shown by putting a second weight on that little kind of piston-like thing, okay? Notice you're supposed to see kind of a bluer color, showing increased concentration, increased solubility of your gas solute, okay, increased concentration of your gas solute. Okay. And Henry's law constant could be figured and used here to predict what the new concentration is based upon the new pressure. All right, so let's do a problem. So just to kind of make sure we're all on the same track, I will hold this up for you, and right under the Clausius-Clapeyron plot, okay, or Clausius-Clapeyron equation, this is what we're talking about here. Okay, so basically we're given a lake, an isolated body of water, and it says with regard to the gas oxygen, the partial pressure at that elevation over that, in the headspace over that lake is 0.14 atmospheres. And they want to know what is the maximum amount of oxygen in parts per million that can be dissolved in this lake. And they go ahead and and they give us the Henry's law constant for that gas in water at that temperature. The only catch, 25 degrees Celsius, that's cool. But the only catch is our Henry's law constant is given in terms of molarity, or moles per liter of O2 per millimeter of mercury. And the partial pressure of oxygen we're given here is in units of atmospheres. So we're going to have to somehow make that jump. Okay. One of the other things, and it'll kind of shake out as we do this problem, but in the chapter when we talked about how do you describe, I introduced molarity, molality. I introduced molality. That was new. We talked about parts per million, and you're going to want to remember that as long as it is a dilute aqueous solution like this, parts per million is the same thing as milligrams of solute, which in this case is gas, per liter of solution. So we're going to make use of that too. So let's see how this one works out. So we're going to use Henry's law. The concentration of the oxygen dissolved in Bear Lake is equal to that Henry's law constant times the partial pressure that was given. Like I said, we're going to have to kind of fix the whole units of pressure. And so I can see in my notes that that's actually what I did first. Since Henry's law constant was given per millimeter of mercury, I need to get my partial pressure of oxygen into millimeters of mercury. So, of course, it's an exact relationship. 1 atmosphere is exactly equal to 760 millimeters of mercury. So now I can go ahead and plug that in to, let's not make it harder than it is, right? So basically this term is going to go there, okay? And this term, KH, was given in the problem. So it looks like this. So this is KH, given in the problem. And this is the partial pressure of O2 in millimeters of mercury. And so unit-wise, notice that pressure, millimeters of mercury cancel, and we're left with moles of O2 per liter of solution. So instead of milligrams, I have moles. So this goes back to a Gen Chem 1 thing, right? So to get from units of moles of O2 to milligrams of O2, I can go through grams. I can use the molar mass of O2. And it looks like this. So don't forget O2, the molar mass of O2 is 32.00 grams per mole. And then one last thing, because that will leave me grams, not milligrams. So to get milligrams, I put 1,000 milligrams over 1 gram. And that will get me where I need to go. Kind of a last step. It's like rounding it to two significant figures, and the answer is 5.7 parts per million. 5.7 milligrams of O2 per liter of solution. And that's it. Do one more. One more Henry's Law. So in this case, we're looking at nitrogen instead of oxygen. It's still in water, which is great. They tell us that at 0 degrees, and actually a headspace pressure of 0.790 atmospheres of N2. The partial pressure of 0.790 atmospheres, the solubility of N2 is 8.21 times 10 to the negative 4th moles per liter. So basically they're giving you a pair, they're giving you a C, and they're giving you a P, a partial pressure. The problem goes on to say, what would the new solubility be at the same temperature if now the pressure, instead of 0.790, now the pressure is 1.10 atmospheres? Okay, you figure you're bumping up the pressure, you should be bumping up the concentration too. I've seen some students, and actually some answer keys kind of work this as just ratios, and actually that kind of works. I prefer, and I think my notes here in a minute are going to walk you through using, like I told you, the first C and the first partial pressure to knock out Henry's Law constant, then use that constant with this new pressure to get the new concentration. So if we take Henry's Law, rearrange it for the Henry's Law constant, of course, that KH would be equal to the concentration of the gas divided by the partial pressure of the gas, which we have those. Okay, so putting in real numbers, it looks like this. So the concentration of the gas at that temperature and this pressure was 8.21 times 10 to the negative 4th, or 0.000821 moles per liter. The pressure at that time was 0.790 atmospheres, partial pressure of nitrogen. Divide it out, and you have a Henry's Law constant for nitrogen dissolving in water at 25 degrees Celsius. And you'll want to, keep up with your labels. Of course, now this would be in units of moles per liter per atmosphere. Then we apply it. So the new concentration of nitrogen would be equal to that Henry's Law constant, 0.00104 moles per liter atmospheres, times the new partial pressure of nitrogen, which is 1.10 atmospheres. Rounding to 3 sig figs, and we'll have units of moles per liter, won't we? So the new concentration of nitrogen will be 0.00114 moles per liter. So they're not bad. Have a nice little solubility thing. Just think pop. So let's take a look at these. These will be due Wednesday. But I have 48 crossed out. There must be a reason for that. Can't remember. I didn't look it up. I don't know if you've done it, but don't do 48, okay? 43, 45, and 46. Whatever you do, don't do 48. Makes you want to go do it, though, doesn't it? Okay, so this is what the first one looks like. And I just went ahead and kind of made a beaker of water down here. And here's my headspace, all right? And I tried to seal it with a watch glass, which doesn't seal it very well, but just kind of bear with me. It describes where the partial pressure of partial pressure of O2 in the headspace is 1.00 atmospheres. It gives the concentration of O2 in terms of milliliters of O2 per 1 liter of liquid water down here. Water's your solvent. And then it asks you basically what will be the molarity if you jack up that partial pressure from 1.00 to 3.86 atmospheres. My hint, and I kind of looked at I'll bring that back. My hint is to actually make sure you first get that volume instead of milliliters, get it in terms of moles. And then kind of do the Henry's. Then get the KH. I shall show you what I mean. So I said basically fix it from 28.31 milliliters of O2 per liter of H2O. Get it in terms of moles. And you can use the ideal gas law equation. PV is equal to nRT. Solve for N. Okay. Where your pressure of O2 is the 1 atmosphere, your volume is the 28 milliliters, your R, of course, and your T is given. So then once you have that, you have the moles per liter, and you can kind of do it like we did a problem a little minute ago. Okay, so I would go ahead and get the KH from that, okay, and then apply that KH to the new pressure. That's what I would do. Okay. The next one's talking about natural gas. Don't let the 90% fool you. I kind of read it a few times. I'm like, that 90% has nothing to do with it, okay? So basically it's just saying instead of being 100% methane, we're going to assume that it behaves like methane, CH4. And we have the solubility of CH4 as 0.02 grams of CH4 per kilogram of water, okay? Right there. Concentration of natural gas. Then it says we're going to jack up, let's see, that's 1 atmosphere. Okay, so this stuff is given. So basically, from this concentration, this pressure, you can get a KH, right? And then go ahead and use that KH to jack up from 1 atmosphere now to 20 atmospheres, find out what the new concentration will be, but you're almost done. Because once you have that concentration, it says, all right, at that concentration, how much methane is going to be dissolved in that 1.00 times 10 to the 3rd kilograms of water. So you're going to have to kind of use a factor label to finally get the concentration, use this concentration, the mass of the water, to get the mass of the gas that was dissolved in that mass of water. That's what I would do. And the last one, we kind of have a couple scenarios. They're both with headspace of 1.00 atmospheres. Monkeying with the temperature this time. Remember, Henry's law constant is constant for a particular temperature. Okay? But it's not really Henry's law. I don't think it worked. Basically, they give you this. They give you the concentration of CO2 that will dissolve at this temperature, the concentration that will dissolve at this temperature. And they say, all right, we're going to take 515 milliliters of solvent of H2O and we're going to heat it. And you're supposed to come up with what volume of O2 will be expelled. So basically what I would do is use that 515 and the concentration to get moles here, 515 of this concentration to get moles here, okay? Of course you have more moles at the lower temperature because the solubility decreases with increasing temperature. Once you have moles, get the change in moles by subtracting, okay? And then basically get the volume of the gas by using, this will be the moles that were expelled. Let's see, and I guess the temperature you're going to have to use here is 0 degrees Celsius, and R, and pressure is the constant 1. Okay, so those three. On to Raoults law. Okie dokie. I like Raoults law too. This is kind of weird, a colligative property, because like in chemistry we keep talking about how like the inert gases they don't react, right? And of course the group 1A elements we know react violently, for instance, with water. I mean, what a particle will or won't do depends upon what that particle is, what sort of element that thing is. A colligative property thinks about it totally differently. A colligative property says, I don't care what you are, basically, just that you are a particle. A colligative property is independent of what something is, just that it is there. Okay? A colligative property of dissolving a solute in a solvent says, basically, I don't care what particles those solute particles are, just that they are there. A very practical thing going on right now is when they're trying to treat the roads and make it the ice stay off the roads, okay, they salt them down. But you know, historically, they could put any sort of particulate out there. Okay. All right. So one sort of, not only are we able to lower the freezing point temperature of water, and we'll talk more about that on Wednesday, but another thing is if you sprinkle a solute in a liquid solvent, or it could be a liquid solute. If you add a solute to a solvent, that solvent will have a lower vapor pressure than it had before you added stuff to it. It's called vapor pressure lowering. So the pure stuff always has the highest equilibrium vapor pressure possible. You start adding stuff and it goes down. And we'll talk about why that is right now. The not means pure, and the without not means something's been added to it. Okay, so that's important. That means pure. And without means solvent plus solute. All right. So deltas are always about final minus initial, and we're going to keep with that. And we're going to assume that you start out with pure stuff, and it makes sense, and you add something to it, and you get the solution. Okay, so the final actually is P. Does that make sense? Okay, and P naught is the initial. So make sure we're all kind of on the same page here. This would be P naught, and this would be P. I guess I should explain what these P's are. That is actually the equilibrium vapor pressure. These P's are the equilibrium vapor pressure of the pure stuff versus the equilibrium vapor pressure of the stuff that something's been added to. Okay. So it's always final minus initial. So that's why the delta P's are the equilibrium vapor pressure of the solvent that has stuff added to it. From that, you subtract the equilibrium vapor pressure of the pure stuff. And the pure stuff was higher, so guess what? These are always going to be negative. Yep. You got it. And let's see if those are on here yet. Not yet. We're getting close. Okay. Okay. So, you guys, and actually, finally at the end of Unit 1 is we're getting around to some of those. We had that unit on solution concentration, okay, with introducing molality and mole fraction. You guys are going to be using mole fraction here, okay? Now, there's a lot of S's, so keep your wits about you. Okay, basically, they're saying that the partial pressure of the solvent that you added solute to, partial pressure of it, is proportional to, that's what that symbol means, the mole fraction of the solvent in that mixture. That makes sense. Seems reasonable. And one of the things we know about proportionality symbols is we can replace them with an equal sign if we introduce a constant. I'm going to replace that constant here in a minute. But just for kicks, we're replacing the proportionality symbol with an equal sign and introducing a K constant. So it's just basically saying whatever equilibrium vapor pressure that solvent in that mixture can have is equal to some sort of constant times the mole fraction of that solvent. So this is kind of a little thought exercise. So the mole fraction of the solvent, let's say we keep increasing the mole fraction of the solvent. Now, the highest mole fraction you can have is 1, right? A mole fraction of solvent of 1 means basically there's no solute in it, right? In that case, basically, the equilibrium vapor pressure of our solvent is equal to P naught. Does that make sense? Okay. So what we have here basically then is we can replace, instead of that kind of random constant K, we actually, for that particular solvent, can put its pure equilibrium vapor pressure, P naught. So this is actually the form, this here in the blue box is the form of the law, and this is called Raoults' law. This is the form of the law that we use. So again, it was very important that we're all kind of on base, knowing whenever you see a P naught, I'm hoping you think pure solvent. Okay? And over here without the naught means it's a solvent with a solute. So the solvent with the solute, the equilibrium vapor pressure, is equal to the mole fraction of the solvent times what it would be if there was nothing happening. So you get this from a table, by the way, okay, the P naught. So, all right. So way back, seems like forever ago, we talked about solutes dissolving in solvents. We talked about an ideal solution. That was one where the energy associated with breaking the bonds of the individual solute and solvent is equal to the energy, that energy is required, is equal to energy released when new bonds are formed. That's ideal. So Raoults' law is supposed to only apply to ideal solutions. Down here at the bottom it says, but even if the solution is somewhat non-ideal, endo or exothermic, overall dissolving a solute in a solvent, it works pretty good. The middle one there says, and I'm not going to make you think too hard about the middle one, but it is possible. I think. Well, Raoults' law applies to multiple volatile solvents, or multiple components that are volatile in the same solution. So we'll see. All right. So let's look at kind of a thought example. Let's just say you have two stuff thrown together, a mixture of stuff. Okay. If you were to tell me the total mole fraction, they equal 1. Okay, that makes sense. Well, we can break out and look at the partial pressure of A the partial pressure of B individually. And according to Raoults law, and actually this would be that middle criteria on the previous slide, the partial pressure in each case is their mole fraction of how much is present there times how much they would, the equilibrium vapor pressure of their pure stuff. Mole fraction of how much is present times the equilibrium vapor pressure of pure stuff. Okay, so you can get the individual partial pressures. And of course, the total pressure is equal to the sum of those two partial pressures. So, by definition, something is not volatile, non-volatile, not volatile, non-volatile, if it generally will not just kind of tend to go from a liquid to a vapor. Okay? Or will not tend to go in the vapor phase, I guess I should say. Most oftentimes when we get rolling using Raoults law, our problems are going to be such that a non-volatile substance has been added to something that is volatile. Okay? So that would mean that for that component that's not volatile, its partial pressure is 0. Let's do one of these. I think this one should be too bad. Okay. All right. So I'm not going to draw a picture, I'm going to fold my hands up. Okay. So this is my 100 grams of water. Okay. My glucose, do you think glucose is volatile? I don't think so. That's my non-volatile solute that I'm going to dissolve, given the mass, given the formula of glucose, because you're going to need that, okay? So given the mass of glucose, given the mass of water, we're supposed to come up with what the new equilibrium vapor pressure would be at 90 degrees Celsius. By the way, there's a table coming up here in a minute that you could pick out 90 and you could see at 90, without any solute added, water has an equilibrium vapor pressure of 525.8. Okay, so that's going to be our P naught, isn't it? And there's our P naught. Now the catch here, or it's not really a catch, but here's Raoults law. This is what we're going to use. I guess to me the biggest catch is we need to come up with a mole fraction of water. Mole fraction of solvent. That's the hardest part here. And it's back to kind of Gen Chem 1 stuff. Okay. So we need to get the moles of the glucose. Is it glucose? Divided by the moles of glucose plus the moles of water. Nope, I told you wrong, sorry. The moles of the water divided by the moles of the water plus the moles of the glucose. So that's what these slides do. I'll just put all these up here. Oops, sorry. You probably recognize from Gen Chem 1 the mass of the water, the molar mass of water to get to moles of water. The mass of the glucose, the molar mass of the glucose to get the moles of the glucose. And then it's kind of all downhill from there. But you heard me mess up a minute ago, so don't you mess up. It's the mole fraction of solvent, which is water. So then the X here looks like this. It's that 5.549 moles divided by quantity 5.549 plus 0.0278. And then that is what we're going to plug in for X. We just multiply. And one of my things I like least is knowing how to round those. 4 sig figs, 0.9950 is the mole fraction of water. So then all we got to do is plug in. So the equilibrium vapor pressure of the solution is equal to that mole fraction, 0.9950, times P naught, which is 525.8 millimeters of mercury. Round to 4 significant figures, and that's it. 523.2 millimeters of mercury. It never hurts to take one more look at it. This one should be lower than the P naught. And it is. I guess it will always be lower if the mole fraction is less than 1. So yeah, this is where this then obviously is this one right here, right? So left. Okay. So I actually have these posts ready to go. So I'm going to go ahead and make these due Wednesday only because I care. I think it would be good if I wait to sign them Wednesday and your test on Thursday. That's not nearly as helpful. But this is basically what you're going to run into. 53 looks like this, where it's glucose dissolved in water. They give you the mass of the glucose, the mass of the water. It's kind of like the example we just did. That one's not too bad. This one, it's dissolving urea, not in water now, in methanol, which is kind of exciting. Methanol is your solvent. And my hint here in green is basically I would use as your basis 100.0 milliliters of methanol, only because that is how the urea is described as being 17 grams of urea will dissolve in 100 milliliters of methanol. So use that as your basis and kind of let things fall into place. The density of methanol is given so you can get to the grams of methanol, so you can get to the moles of methanol. And the last one's kind of fun too. Basically, you don't need a calculator for the last one, I don't think anyway. And it gives you 2 solutions. One has sludge at the bottom and one doesn't. So we talked about what sludge means, right? Sludge means it's saturated. So this one on the left is saturated, that one on the right is not saturated. And then asking a few questions, for instance, and I would put like a little watch glass over the top. So what is the equilibrium vapor pressure in the headspace above that liquid with regard to water? Okay. So kind of think in context of what we've been talking about, what that would look like. So I will post both of these before I go home tonight, because sometimes I forget. But you got my number. Let me know if you have any questions.